Well, hello everyone, and welcome to your daily dose of DOE. And my screen sharing is not working right here. Let's get that back. Okay, this is not, okay. There we go. Sorry about that. Welcome everyone to your daily dose of DOE here at the 2020 Online DOE Summit, sponsored by Statties. And today we have Mathijs Uljé, who's going to be presenting using experimental design to optimize the surfactant package properties of a metalworking cleaner. And let's see, so, okay. All right, Mr. Uljé is a development chemist 2 at Quaker, Houghton, and has been there for a little while, and you can see his background and areas of research listed there. And he's going to be talking about his research. Now, during the talk, you may come up with some questions. Feel free to type them into the questions area in the menu on the right-hand side of your screen. And at the end, we'll have some time for a Q&A session. And I will go ahead and read out those questions, and we'll get them answered for you. So let's see. Oh, I should also say that later today, we will get these slides posted up onto the Statties website, and the recording for this will also be posted up later in the day. So without further ado, I will hand it over to you, Mathijs.
All right, thank you. Welcome. I will be giving my presentation about using experimental design to optimize the surfactant package properties of a metalworking cleaner. First, I would like to introduce you to the beverage can manufacturing process. This process starts off at the front end. This is where we as Quaker Houghton supply a few of our process fluids. We start off with a sheet of aluminium. This sheet is protected by a post-loop oil. This oil gives corrosion protection and lubrication performance in the later on process. This sheet is then transferred to the copper. Here a cup is drawn from the sheet material. This is done by the help of a cupping oil, and this oil provides mainly lubrication to the drawing process. This cup is then transferred along to the body maker. In the body maker, the cup is narrowed and elonged by redrawing and ironing deformation. This is done with the help of a coolant. This coolant will provide cooling to the process and additional lubrication. This can, which is then a little bit dirty of the coolant fluid, is transferred to the washer, where it is cleaned and protected against eventual or possible discoloration of the aluminum surface. This is done by a metalworking cleaner, and this cleaner is responsible for removing the coolant and etching of the aluminum surface. This clean can is then transferred on to the back end, and in the back end process it starts with a decorator. In the decorator, the clean can is labeled by paint application, and in this application very clean can is very important, because a clean can will provide a good wetting of the paint and also adhesion of the paint, which is very important. Then this can is transferred to the inside lacquer. Here the can is provided with an inside coating, and this coating will also prevent the aluminum from corrosion when a beverage is introduced into the container. Also here, a clean can is very important for proper coating, wetting and adhesion. This can is then transferred to the necker and flanger. The necker will provide narrowing of the top of the can, which will provide strength to the structure, and a flange is applied, and on the flange the top lid can be mounted when a beverage is inside the container to close it up. This will the closing and beverage will happen at the beverage manufacturer. The final output of a beverage can manufacturing plant is about 3,600 cans a minute, and the production runs 24/7 almost all year around. So that's an output of millions of cans per plant per day. Now I would like to talk about the washer process. This is where our cleaner is applied. This is a scheme of the beverage can washer. As you can see here on the left, the dirty cans will enter the washer. This happens in very large numbers, as you can see in the picture below. In the first two baths, the cans will be rinsed, first with just plain water and then with slightly acidic water. Here a lot of the contamination on the can will be already removed, but there's still some significant contamination on the surface. The further process will go to stage 2. This is the washing stage. Here our cleaner is applied and the can will be completely clean after stage 2. However, also in the further stages, there will be a rinsing stage to remove the excess amount of cleaner on the can. And then it will be transferred to a treatment stage. Here a so-called conversion coating is applied, and here the can is protected against discoloration in the further process. Then another 2 rinse stages to make the can even more clean without residues of products. And in the end, a mobility enhancer, which will provide a little bit of lubrication when transferring the clean cans to the back end, or first the decorator. Now I would like to go further into detail in the washer, about stage 2, the washer, where our cleaner is applied. Our cleaner technology. So 3 very important aspects of the cleaner. That is, first, good cleaning performance. So removing all the debris from the surface. It has to have a low foaming performance and preferably no foam. And also a good oil separation. It needs to split out the oils which it cleans off the surface, because by splitting them out, the cleaner will maintain its good cleaning capabilities. The composition of a cleaner, it mainly consists out of water, and from 30 to 65% approximately. Also a large amount of sulfuric acid, and about 8 to 12% of non-ionic surfactants. These non-ionic surfactants are mostly in the product as a package of 2 to 3 different non-ionic surfactants, which each having their own specific property. The properties of the cleaner. The first one is the removal of dirt. This is mainly done by the surfactants. And the dirt consists mostly out of mineral oils, heavy and light ones, so thick or thin oils, fatty acids, esters, and aluminum particles. And also another important property is etching of the aluminum. This is done by the acids inside of the cleaner. This will provide a new aluminum surface. The non-ionic surfactants. A surfactant stands for a surface active agent. This is an amphiphil compound. That means that it consists out of two groups. As you can see here in the picture, it has a tail. This is the hydrophobic tail. This tail loves to be in an oily environment. And you have the hydrophilic head. And this head loves to be in water. What this does is that the surfactant will collect on the surface of the water. By collecting on the surface of the water, it will lower the surface tension. This will provide wetting properties of the cleaner. And this is very desirable. As you can see here in the picture, when you have no wetting or a bad wetting, the droplet will remain as a droplet on the surface. But with good wetting, so with the introduction of surfactants, the droplet will spread out on the surface and you will increase your contact area, which is beneficial for the cleaning process. When the surface of the water is saturated with surfactants, they are able to go into solution. This is called the critical micelle concentration. At this point, also micelles can be formed in the cleaner solution. And these are very important to provide cleaning properties. By emulsifying the oil in the cleaner, you will clean the surface. Another important aspect of non-ionic surfactants is the cloud point. The cloud point is temperature dependent, and it's a temperature above which a solution of a non-ionic surfactant becomes turbid or cloudy. This has a significant influence on the foaming and cleaning properties of the cleaner. Especially the foam is highly influenced by this behavior, because when you are testing your cleaner above the cloud point, the foaming properties will decrease rapidly. And when you are below the cloud point, you will see an increased amount of foam. This has to do with the solubility of the surfactants. The problem statement. Our existing cleaner. Our existing cleaner shows a good cleaning performance. However, it also shows a little bit too much foam. And this excess amount of foam is suspected of contaminating the other stages in the washer. The foam can be dragged over by the cans and the conveyor belt. And with the foam, also debris from the cleaning bath is transferred to the other baths. In the end, some stages end up contaminated with oil, and this will precipitate on the can surface and causes a de-wetting, which is not desired for a good paint wetting in the decorator. Our current cleaner exists out of a package of 3 non-ionic surfactants. The goals for the new cleaner. Of course, to maintain a good cleaning performance, but lowering the foaming behavior. And we want to do this by optimizing the existing surfactant package. The design setup, with the help of design expert. The formulation contains 3 non-ionic surfactants. These are shown here in the table, component A, B, and C, and they each have their own property. So you see a low cloud point surfactant, component A, and B being a medium cloud point surfactant, and C being a high cloud point surfactant. These components are all varied in the mixture design from 0 to a maximum of 10%, but they will always add up to a 10% of total surfactant in the product. And the remaining 90% is a standard mixture of water and sulfuric acid. For the model, it was chosen to go with an augmented simplex lattice. This is chosen for its actual check blends and its overall centroid. This way, we could properly assess the lack of fit in the model. It's chosen for a quadratic design and 17 runs in total, of which 10 are unique and 7 are replicates or duplicates. The response tests. The first one is the cruise dynamic foam analyzer. With this equipment, we can measure the foam height in millimeters. This is done by purging a controlled amount of air through the cleaner, and by that, foam is created and the foam height is measured by the equipment. Second test is the can cleaning lab test. This test gives 3 responses. The first one is the cleaning response. This shows the water break on the cleaned can in percentage. So you can imagine that a dirty can will break up the water after cleaning, and then you can say that the can is not clean. But if the water layer remains intact on the clean can, you can say that it has a perfect cleaning. Also in the cleaning test, you can read the amount of foam in the bath, and this is also expressed in foam height in millimeters. And also the cleaning can be tested in a second way, and that is measuring the internal brightness of the cleaned can. You can imagine that a dirty can has a lower internal brightness compared to a very clean can with a shiny surface. This will give a higher internal brightness. And the last one being the cloud point response. This is a theoretical approach. For each formula, the cloud point was calculated, and this is done for the final optimization process. For the optimization process, I wanted to set a minimum cloud point. This is desirable because you don't want the cloud point to be too low in comparison to your actual temperature, which is in this case we always run at 60 degrees. And if you are too low, then the surfactants will split out. And eventually this will lead to the depletion of surfactants in your cleaner bath, and this will influence the cleaning performance of the cleaner, which is undesirable. The first results from the cruise foam test. These results could be fitted into a special quartic model, but the ANOVA showed a significant lack of fit. This is not desired because we want the lack of fit to be not significant, because we want the data to fit the model, of course. The box-Cox plot showed a too high lambda. This is also undesirable. For this reason, a square root transformation was applied on the data. This gave the following ANOVA table. As you can see here, in the end, we ended up with a model with this very low p-value, which means that the model is significant, and a higher p-value for the lack of fit. So it means the lack of fit is not significant. So this is good. The fit statistics are shown on the right. Here you can see that I ended up with a very high adjusted R squared and also a high predicted R squared. The difference between them is very small. So this gives enough precision to navigate the models with high accuracy. This is also shown in the predicted versus actual graph. Here you can see that the predicted values and the actual values are very close to each other, giving a high accuracy in the model. These are the model graphs. These are very visual, and there are already a few observations we can take from these graphs. The first ones being that both component A and component B both show a very low foaming performance. So this is very good. We want as low foam as possible. However, when you introduce component C, you can see a significant increase in amount of foam, which is undesirable. The cleaning results. These results could be fitted into a special quartic model. However, this gave bad fit statistics with a low predicted R-squared, and the difference with the adjusted R-squared was higher than 0.2, which makes the navigating the model inaccurate. Also, the box-Cox plot showed a too high lambda. For this reason, and also a model reduction was applied. This gave the following ANOVA table. As you can see here, again, a low p-value, which gives a significant model. This is good. And a higher p-value for the lack of fit. So the lack of fit is not significant. Also, the fit statistics are much improved after adjustment. You can see that the adjusted and predicted R-square are both high, and the difference between them is lower than 0.2. So this gives enough precision to navigate the model. This is also shown in the predicted versus actual graph. Here you can see that the difference between the predicted and the actual values is quite low. So the model can be navigated with enough precision. This gave the following model graphs. Also from these graphs, these are very visual and we can already take some observations from this. What we can see at first is that component A shows a very bad cleaning performance. As you can see here, when you have products based on component A, or mainly or only composed out of component A, show a very high water break. This means that the can is not cleaned off properly after the cleaning process. You can see that when introducing or basing a product on component B will already increase the cleaning performance somewhat. However, this is still not perfect. This is still, it's a decent cleaning, but not good enough. What you can see for component C gives a very good cleaning performance without a water break on the surface. The foam results from the cleaning test. These results could be fitted into a special quartic model. This ANOVA showed a significant p-value and a not significant lack of fit. So this is very good. This is what we want. But the model graph showed possibilities on getting negative prediction values. For that reason, square root transformation was applied, and also it was fitted to a quadratic model. This gave the following ANOVA table. This ANOVA shows low p-value, which makes the model significant, and also a higher p-value for the lack of fit, so that makes the lack of fit not significant. This is good. And the fit statistics show a high adjusted R-squared and predicted R-squared, and the difference between them is again lower than 0.2. This can also be seen in the predicted versus actual graph. Here you can see again that the difference between predicted and actual values is very low. This gives high precision in navigating the model. Here we see a familiar image. This is very comparable to our cruise foam results. It shows the same trend, which is that both component A and B show very low foaming properties, and when introducing component C, the foaming properties will go up. But we also saw, of course, with the cleaning results, that component C is very beneficial for the cleaning performance. So it means that we at least need some of the component C to achieve a proper cleaning performance. So this is where the balancing will happen. The internal brightness. The results from the internal brightness measurements could be fitted into a special cubic fit. However, they showed a low predicted and adjusted R², and the difference between those were larger than 0.2. This gives low precision in navigating the model, which is not sufficient enough. Several data transformations or model reductions were applied, but this did not significantly improve the statistics. It is known from experience that the internal brightness measurements can have some inaccurate values, and it is sometimes difficult to have accurate repeatability with this test. So this is now also shown in the statistics, as we see. This is also seen in the predicted versus actual graph. Here you can see that there is a larger difference between the predicted and the actual values. This makes the model less accurate and to navigate. It showed the following model graphs, and also in these graphs you can see that there is quite a large difference between duplicates in the points. So this will give a lower accuracy in navigating the model. Some things we can see from this model is that there's no significant difference between component A and B, but it seems that the brightness does go up when we are basing products on component C only. However, we decided not to take along the internal brightness response in the optimization process due to lack of fit statistics. The optimization process. So the first optimization process. The goal was to minimize one of the goals was to minimize the foam. So with the first optimization, I set the goals of both foam responses to minimize with the highest importance of 5. Then I set the cloud point to a lower limit of 40 degrees and the upper limit of 55 degrees, so that we are always above the cloud point, but not below 40, because that is then it becomes risky of splitting out the surfactants. This optimization gave two solutions, with the first one having the significant higher desirability. So this was chosen for further testing. As you can see, this solution consists mostly out of component B and some of component C, which will probably be introduced to enhance the cleaning performance. Then the second optimization. This optimization is more or less the same as optimization 1. However, I increased the cloud point with 5 degrees. This is to be even more sure about a decent cloud point without the risk of the splitting of the surfactants. This again gave two solutions, with one having the significant higher desirability. And what you can see here is that again, most of the formula consists out of component B, but now also a quite significant amount of component C. Then the last optimization conditions. Here again, both foam responses are set to minimize with the highest importance of 5, but now also the cleaning performance was set to minimize, but with an importance of 3. This gave 4 possible solutions, with the first one being chosen because it has the highest desirability. This again shows a large amount of component B, and this in combination with a significant amount of component C. Then also solution 2 was chosen because this is the only solution which incorporates component A. And I was curious what that will do to the product performance. In the end, I ended up with 4 optimized products, which all vary a little bit from each other. So what you can see here is that mainly the first 3 formulas will show, the first one shows the highest amount of component B, and you can see that it slowly decreases in the first 3, and that component C increases. And the last one is similar to the third product. However, some of component B has been replaced with component A. These are the predicted values for the formulas, and all 4 formulas have been tested again in the response tests, and these are the measured values. These values have been compared to each other. The values were not the same. However, they showed a similar trend. As you can see here, you see an increasing trend in foam when you go from formula 1 to 4. And this is also shown in the measured values. You can see that formula 1 has the lowest foaming property and formula 4 has the highest foaming property. Also with the cleaning, you can see that the first formula has the worst cleaning performance. However, it turned out to be significantly worse than predicted. This could have to do with the narrow line of the cleaning performance, that we were just outside of the cleaning performance. And what you can see with the other 3 formulas is that the predicted values are quite close to the measured values. Also the reference, the current product, was measured. And when comparing these results with the optimized formulas, I decided to go with the second formula as the best one. This shows a low foaming performance, still a good cleaning, and a cloud point of 40 degrees. This product was then tested with a trial, and indeed it showed a lower foaming performance and still a good cleaning performance. A summary of the project. Some main conclusions can be taken from this project. The first one's having to do with surfactant behavior. What I learned from this project is that a low cloud point surfactant gives a low foaming performance. However, it also shows a bad cleaning performance. And the higher cloud point surfactants will give a high foaming performance, but also a good cleaning performance. So these two have to be balanced out with each other. This was of course done by the optimization, and this gave in the end a product with a low foam profile and a good cleaning performance. And in the end, it turned out that we only needed 2 surfactants in the product. This was something I did not expect and probably would not have figured out without the help of the DOE. So in the end, the experimental design proved to be a success in the optimization process with a very efficient work and minimal amount of work. We had the maximum amount of output. This was very nice, and this resulted in a very fast development of a new cleaner product. And it turned out that the design expert software was of essential help with the whole project for the design setup and the data analysis, and also in the optimization process. It was very helpful to have the software. And also the graphs from the software are excellent presentation material for internal presentations, information sharing, or even for our sales department in promoting and selling the product to our customers. I would like to thank you all for attending this presentation. And I would like to give my special thanks to Jason Pandolfo. He has been our trainer in the statistics and design of experiments, which he does very good, and he's been of great help in the whole project and in the preparation of this presentation. So I would like to thank him for that. If you have any further questions or comments, please don't hesitate to contact me on my email or by phone. Thank you.
Awesome. All right. Thank you, Mr. Uljé. Let's see. I'm going to take back. I'm going to show everybody a couple of things. We're going to do a little housekeeping here. Couple of points to cover. Let's see. Whoops, let me get to the right page. First of all, oops, I forgot to change this slide. Just ignore this slide, everybody. Let's see. One thing, we are running a special right now on all of our distance learning workshops. We have a special price on them right now. That slide, for some of you who have attended some previous presentations, you might have seen a coupon code to enter. You don't need to do that. We just drop the price across the board on all the workshops now. So you will see that if you're interested in learning more about DOE, and you can head over to staties.com and look in the Learn DOE section of our website to find what's going on with current classes. And some of that information will also be in a follow-up email, as well as where to find the slides and the video for today's presentation. The slides have now been posted up onto the website, so if you have some questions right away afterwards or wanted to review a slide, you can feel free to go over to staties.com and look in our webinar section. So now we'll run through some questions. As I said earlier, feel free to type those up into the questions area in the menu on the right-hand side. And let's take a look. Let me open up that section. Okay. Okay. Let's see what we have. Okay, for the first question from Naresh Kashiraskar is, what is the importance in the design software? How do we select a 5 or a 3 or a 4?
Yeah, that's a good question. The importance, I'm not 100% sure, I have to admit, but I think it gives a priority to a specific response. So it will rank the foaming performance, for example, in my design above a cleaning performance. So it will give a higher desirability to a formula with a higher cleaning or a better foaming performance in comparison to a better cleaning performance. So I think it's just prioritizing the responses in your optimization.
Okay. Let's see. Next question is from Thorsten Peich. He says, thanks a lot. How did you decide which transformation to use?
Thank you. And yeah, the decision on the transformation has been chosen by sometimes by the fit statistics, of course. The lambda value was important for this. Also, here the software will also show you that transformation is advised, and you can also of course experiment with different transformations and see how the fit statistics will improve and values in your ANOVA table. And in the end, also, like I said, the software will advise, and I saw that it helped in improving the fit statistics and ANOVA table results. So that's how I have applied it in my experimental design.
Okay. The next question is from Yoon Han, and they ask, by including both foam measurements in optimization, are you overemphasizing this response, essentially counting it twice?
That is a good question, which I'm not 100% sure of. I don't know if it will add up in the optimization process. I think for us it was also done as a confirmation, because we have the cruise test, which is dedicated foam testing, and we already did some R&R studies on this, and it turned out to be a quite accurate test, especially in a nice controlled cleaner environment. But we also would like to know if our cleaning test would show significant and trustworthy foaming results. And by looking at the data, and the data showing similar results for both tests, turned out that we can also look at our foaming behavior in the cleaning test. But with the optimization and including them both, I'm not sure if they will add up in the optimization, and so I will I cannot give you the answer on that, but I can look it up and give you the answer later maybe.
Okay. Next question is from Elke Schlosser. In one of the responds, the model was reduced. How was this done?
This is done with the help of the software. It advises you also to reduce the model in order to improve the statistics. So this can be done, and then you can see that indeed the model has been improved. So yeah, again, the software was a great help in this, in improving the model, and then you just have to take a close look and a good look at the values and see what the optimal conditions are for your statistics.
Okay. Next, Randy Nides writes, did you know that high foam correlated strongly with cleaning before starting the experiment?
Yeah, that's a good question. I was somewhat aware of it. I think it also has to do with the chemical structure of the surfactants, which I cannot share, unfortunately, because of secrecy. However, I already had a suspicion that surfactant will, with the higher cloud point, will also provide a better cleaning performance. But I never tested it as accurately as I've done now with this experimental design. So it was more also a big confirmation about the theory behind it. So that was also nice to have it confirmed.
Okay. Let's see. Next, what about the influence of process parameters like temperature, ultrasonic power, etc.? And that's from Marcus Hofer.
Yes, good question. This is all controlled by the test settings, of course. which I have not go into detail with, but it's very valid, of course, because we all want the same test conditions for each response value, of course. So what I've done is that, for example, the concentration of the tests will always be the same. For in this case, 1%. The temperature will always be set at the 60 degrees. And this way, I try to control the variation between the tests and with the whole design. However, these tests are of course done on a certain scale in a laboratory environment, and there will always be a little fluctuation in some parameters which you cannot control or are very difficult to control. However, they turned out it turned out that the values were very significant. Only we saw, of course, with the internal brightness that this was less significant, and that's like I said, a test of which we also know that the repeatability is lower compared to other tests. What this causes, we are not sure, but yeah.
Okay. Let's see. The next question comes from Bet Benedicto. And let's see, they say, thank you, really interesting. Is the water break test a reliable method to check cleaning performance?
Thank you. And I think I have to answer that this is the most reliable for a laboratory test. It has been applied in our industry for many years, and also within the can industry, you can see that the wetting of the surface of the can surface is very important, and that most of the time when you can see problems in the back-end process, it has to do with the wetting, with the water wetting of cans. We are also convinced that when there is enough debris or a significant amount of debris on the surface, this will always result in de-wetting of the water. However, we also are aware that, for example, reading of values in percentage from a surface is quite difficult. So this takes a lot of experience and training, and it is also beneficial to have it done by someone who is very trained and has a lot of experience with this test to give a good estimation of the amount of wetting on the surface. But yes, it can give some inaccurate results, and it is a difficult test, I have to admit. But the difference between a completely clean can and a slightly dirty can can always be observed, in my opinion.
Okay. Let's see. I think we can do a couple more.
Yes.
Let's see. Okay. This one is from Jom Jossa. Thanks for the good presentation. And he asks, why did you not include a response with oil splitting capability of the cleaner?
Thank you. And that's a very valid question indeed. I did not included it because at that time we were mainly focusing on the foaming and cleaning performance of the product. And we did not have a validated method for an oil splitting properties yet. This is still under development, but in further development of cleaners, I would certainly would like to take along an oil splitting method. So yeah, it's very valid, and I think for our future projects it will be included for sure. Yes.
Gotcha. Okay. And let's see, last question from Jeffrey Maxwell. How does the software warn you of too much experimental error?
It can warn you in several ways. Of course, by the ANOVA table, p-values will show you inaccurate models or lack of fits. This is already a warning sign. But also in the fit statistics, you can see that the predicted and adjusted R-squared are shown, and the difference between them as well. And the software will also indicate that when this delta is larger than 0.2, it warns you that models cannot be navigated as accurate as you might want it to be. And also with the diagnostics, you can observe regression models, graphs, which you can also read some inaccuracy, and also the lambda, for example. And also here the software again shows that when the lambda value is out of boundaries, it suggests a certain transformation of your data. So there are several ways to, and there will probably be even more ways, how the software helps you and how can you by yourself see that the data is not accurate enough.
Okay, perfect. Well, thank you, Mathijs. That was a very interesting presentation. Gave me some insights into not just the cleaning of the cans, which didn't really think too much about now, but now I will. And the process behind it, that was awesome, and a great use of DOE in optimizing your surfactants. Anyway, so thank you for that presentation. I really appreciate it.
Yeah, thank you for the time. Thanks.
Yeah, and thank you everyone for showing up to this. And we have one more presentation tomorrow in our online DOE Summit, and we hope to see you then. So have a great rest of your day. Thanks, everybody. Take care now.